Quantum Electrodynamics. Quantum electrodynamics, or quantum electromagnetism, is a theory in physics that explains how light and matter interact at the quantum level. It is one of the most precise and successful theories in science, providing accurate predictions about the behavior of particles like electrons and photons, the fundamental particles of light. Despite its complexity, we will break down the key concepts of quantum electrodynamics in layman's terms to make it more accessible. At its foundation, quantum electrodynamics describes how charged particles, such as electrons, interact with electromagnetic fields. Electrons carry a negative charge, and they interact with photons, which are particles of light. Traditionally, light was understood as a wave, and electrons were treated as distinct particles. However, in quantum physics, light can behave both as a wave and as a particle, and the same principle applies to electrons. This dual behavior is known as wave-particle duality, a fundamental concept in quantum mechanics. Quantum electrodynamics operates within the framework of quantum mechanics, a branch of physics that deals with the behavior of particles on the smallest scales, such as atoms and subatomic particles. Unlike classical physics, which describes large objects like planets or cars with predictable motions, quantum mechanics describes a world of uncertainty and probabilities. In quantum physics, particles don't follow fixed paths. Instead, their behavior is described in terms of the probability of being in various states. One of the key ideas in quantum electrodynamics is that interactions between particles occur through the exchange of force-carrying particles called photons. Imagine two electrons coming close to one another. Both electrons carry the same negative charge, and like the repulsion between two magnets with similar poles, the electrons will repel each other. According to quantum electrodynamics, this repulsion occurs because the electrons are exchanging virtual photons. These are not real, visible photons like those that make up light, but temporary particles that only exist during the interaction, pushing the electrons apart. This concept of force carriers is crucial to quantum electrodynamics. In the case of the electromagnetic force, the force responsible for electricity, magnetism, and light, the photon is the carrier of the force. Other fundamental forces in nature, such as the strong nuclear force or the weak nuclear force, also have their own force-carrying particles, but quantum electrodynamics specifically focuses on the electromagnetic force and the way it affects charged particles like electrons. One of the most remarkable aspects of quantum electrodynamics is its ability to make incredibly precise predictions. It allows physicists to calculate the behavior of electrons and photons with an accuracy that matches experimental results to an astonishing degree. This precision is one of the reasons quantum electrodynamics is considered one of the most successful theories in the history of physics. The development of quantum electrodynamics was the result of contributions from several notable physicists. Richard Feynman, an American physicist, played a significant role in advancing the theory by developing a new way to visualize quantum interactions. He created what are now known as Feynman diagrams, simple representations that help physicists understand and calculate the interactions between particles. In these diagrams, particles like electrons and photons are shown as lines, and their interactions are represented as points where the lines meet. Feynman diagrams help physicists visualize how particles exchange photons and interact with one another. Feynman's work, along with contributions from other physicists like Julian Schwinger and Shinichiro Tomonaga, formed the foundation of modern quantum electrodynamics. The theory not only explains how light interacts with electrons but also how these interactions give rise to the electromagnetic forces we observe in everyday life. It offers a framework for understanding the forces that govern the behavior of all charged particles, including electrons, protons, and ions. In quantum electrodynamics, the strength of electromagnetic interactions is determined by a number called the fine structure constant. This small number dictates how strongly charged particles like electrons interact with photons. Since the fine structure constant is relatively small, most electromagnetic interactions are not very strong, but they can still have significant effects over long distances. Another important concept in quantum electrodynamics is the quantum field. In classical physics, a field is something that fills space and affects any objects placed within it. For example, an electric field created by a charged object influences other charged objects in its vicinity. In quantum electrodynamics, the electromagnetic field is treated as a quantum field, which follows the rules of quantum mechanics. These quantum fields can create and destroy particles, which is why photons, the carriers of the electromagnetic force, can be generated and absorbed by particles like electrons. The principle of uncertainty also plays a central role in quantum electrodynamics. In quantum mechanics, particles don't have definite positions or velocities until they are observed or measured. Instead, they exist in a range of possible states, and only when we look at them do they collapse into a specific state. This uncertainty is an essential feature of quantum physics and applies to the interactions between particles and fields in quantum electrodynamics as well. One of the challenges in quantum electrodynamics is dealing with infinities that appear when calculating interactions between particles. For example, when physicists calculate how two electrons interact, they sometimes get results that include infinite values, which don't make sense. To solve this problem, physicists use a technique called renormalization, which removes these infinities and produces finite, meaningful results. Renormalization is a crucial part of making quantum electrodynamics work and ensures that its predictions match experimental observations. Quantum electrodynamics has been remarkably successful in explaining several previously unexplained phenomena. For example, it accurately predicts the Lamb shift, a small difference in energy levels in the hydrogen atom that couldn't be explained by classical physics. It also explains the anomalous magnetic moment of the electron, a slight deviation in the electron's magnetic properties from what classical theories predicted. The predictions of quantum electrodynamics for these phenomena have been confirmed with an extraordinarily high degree of precision, further validating the theory. In summary, quantum electrodynamics is one of the most successful theories in modern physics. It explains how light and matter interact by describing how particles like electrons exchange photons, which carry the electromagnetic force. Through its detailed framework, quantum electrodynamics provides a precise and accurate description of the behavior of particles at the quantum level. While the theory can be complex, its concepts of force carriers, quantum fields, and uncertainty have revolutionized our understanding of the universe and continue to shape the future of physics.